Each atom contains a dense and positively charged nucleus at the center, and negatively charged electrons occupy certain regions of space around the nucleus. When you study quantum mechanics, you'll learn what these regions of space look like. But for now, it's useful to draw the electrons as if they occupy circular orbits around the nucleus. Now, most atoms contain a mixture of protons and neutrons. The neutrons have no charge, but the protons have a positive charge, and the unit of charge is called the Coulomb, and we represent it by a capitalized C. A single proton has a charge of positive 1.60 times 10 to the minus 19 coulombs, and that's to 3 significant figures. And a single electron has the exact opposite charge of negative 1.60 times 10 to the minus 19 coulombs. If we take an atom of hydrogen, which is the first element on the periodic table, this atom contains one proton in the nucleus and one electron tied to the atom in a region of space close to the nucleus. Now, if we add the charge of the nucleus with the charge of its electron, we get a sum total of 0 charge. In other words, a neutral hydrogen atom. And this is what atoms want to be. If we force this hydrogen atom to absorb an additional electron, so now it has 2 electrons around it, this hydrogen atom becomes negatively charged. And it now becomes a negative ion with a charge of negative 1.60 times 10 to the minus 19 coulombs. It has the same charge as an electron. So what do you think happens if we strip all the electrons away from this atom of hydrogen? What happens to its charge, and what would we call this atom? Well, now we only have one proton in this hydrogen atom, and we already know that a proton has a positive charge of 1.60 times 10 to the minus 19 coulombs. And we can also represent this as a positive E, or opposite to the charge of an electron. In principle, any neutral atom can be turned into a positive or negative ion by ensuring that there are more electrons than protons in the atom, creating a negative ion, or more protons than electrons in the atom, making a positive ion. Now, the charges of these ions are quantized. This means that their charges exist in discrete amounts. For example, we can have positive or negative E, or positive or negative 2E, and E is simply the charge of an electron. An ion will never have a charge of 1.48 E or negative 0.12 E. We can only have integral multiples of the charge of an electron. So if you decide to study undergraduate experimental physics, you will do an experiment called the Millikan oil drop experiment, and you'll do this in your first year. This experiment demonstrated that electric charge is quantized, meaning it exists in discrete units, and that the charge of an electron is a fundamental constant. Atoms in metals have one or more outer electrons which are not held tightly to the nucleus. This means these electrons can wander at random throughout the metal, and we typically call these electrons free electrons or mobile electrons. So if I draw a simple diagram of a circuit here, we've got a battery at the bottom, and the battery terminals are connected to a metal rod. When we connect the battery across the ends of the metal, the free electrons within the metal will be attracted to the positive terminal of the battery. and will slowly drift towards it. We'd also find that electrons from the battery, from the negative terminal, will flow into the metal to replace the electrons leaving the metal rod. And this produces an electric current. Now the charge carriers here are electrons within the metal. But could we create an electric current with something other than free mobile electrons? Say if we have a solution of salt water, for example, instead of a metal rod here. So how about using the positive and negative ions that we talked about before? If we're able to get these charged ions to flow to a positive or negative terminal over some period of time, we also have an electric current. When we dissolve salt in water, the solid sodium chloride breaks apart into ions of sodium and chlorine. If we then insert 2 electrodes and apply 5 volts across them, the positive sodium ions feel an electrostatic pull towards the negative electrode, and the chlorine ions get pulled towards the positive electrode. This allows an electric current to flow through the circuit. But the size of the electric current is given by the rate of flow of charge. And the charge here is carried by the positive and negative ions. The more charge that passes through a circuit for a given unit of time, the higher the current will be. We can write this down as an equation. So we've got the current here is equal to the amount of charge passing a cross-sectional area per unit time. So let me ask you a question. So if we go back to our circuit with the metal rod, if we now have 2 circuits with the same metal rod, so the same metal and the same dimensions, but the only difference between both circuits is the voltage in the battery. And I also tell you that there's twice the amount of electrons passing through cross-section 1 than cross-section 2 over a 1 second time interval. What could you tell me about the difference in the current between both these circuits? Because the charge per unit time is twice that of circuit 2, then that must mean the current is twice as large. If we have a look at the formula, if we double the value of Q here, then the value of the current on the left-hand side of the equation will also increase by the same amount, so long as the time doesn't change. The higher the current, the more charge passes through per unit time, and the size of the electric current is given by the rate of flow of charge. So let's try a couple of questions now. The current in the filament of a torch bulb is 0.03 amps. How much charge flows through the bulb in 1 minute? So we already know that the current is equal to the charge over time. And we can rearrange this equation to make the charge the subject of the formula. And we do this by multiplying both sides by time. And time cancels out on the right-hand side of the equation and gets added to the left-hand side. So when we plug in the current and the time in seconds, we get a total charge of 1.8 coulombs. Now, what does this mean in terms of the number of electrons flowing through this circuit? So B, calculate the number of electrons that passes a single point on this filament over the course of 60 seconds. So the number of electrons that flows past any point in 60 seconds is equal to this formula here. So because we already know the charge of an electron, we get a value of 1.1 times 10 to the 19 electrons. Now this large number is the number of electrons crossing a cross-section of the filament. This doesn't mean these electrons have traversed the entire length of the filament in 60 seconds. We're only interested in how many electrons have passed a certain point in the circuit. Now, what you'll find out in a future lesson is electrons in metals move extremely slowly. And I'm talking about speeds less than a millimeter per second, so maybe half a millimeter per second. So let's try another question. Calculate the current when a charge of 240 coulombs passes a point in a circuit in a time of 2 minutes. So again, we can use our current formula, which equals charge over time. And our charge is 240 coulombs, and we're measuring this over 120 seconds. And we get a value of 2 amps.